everybody. So, we're all being quarantined, or self-quarantining, and I'm going to be doing lectures from here in my garage. My wife would be mortified, but I'm going to give you a little look around. Don't judge me. Okay, check it out. Okay, there's nothing interesting anywhere else. Alright, so it's a test to see if I can do this. Okay, I'm going to try an example from Chapter 7. I'm going to try to do these videos in one take, because it's sort of how class goes. I just show up and you show up and we start doing it. So I'm going to try this. This is from Chapter 7. So just an example of how to use cosets to prove something interesting. Okay? Oh, that's my dog, Tommy. Don't do that anymore. That's annoying. Don't mind him. A4, the alternating group on 4 letters. You know what that is. Has no subgroup of order 6. Okay, so let's try this. Proof. Suppose H is a subgroup of A4 and has order 6. Okay, so we're going to try to prove by contradiction, right? Okay, so recall the index of a subgroup in G, although the notation from your book is different, but this is what we did in this. The index of G with H, that's the number of cosets of H there are, right? But we also see from Lagrange's theorem that that's just the order of the group divided by the order of H. Okay, so in this case, the order of G is 12. And the order of the subgroup is 6. So the number of cosets in A4 of this H must be 2. Okay? So there must be a contradiction here. Alright. So, let A be some element in A4, right? Then it's an even permutation. Okay? What kinds of permutations are there that are even in A4? Any 3 cycle will be an even permutation, right? For instance, 1, 2, 3. That's let's see. So 1 goes to 2, and then 1 goes to 3. It's even permutation, right? Because we can represent it as the product of 2 transpositions. That's even number of transpositions. Okay. Now, since the order of h is only 6, there has to be some element that is of order 3 that's not in there, because well, we'll see. If it's in there, then there's a contradiction. Okay, so let's see. So let's do A, H, right? See what that coset is, and then A cubed H, and then H. Sorry, A squared H. All right. So on the one hand, those all can't be all different cosets, because there can only be 2 cosets, right? So this means that either AH is equal to A squared H, right? Or AH is equal to H, or A is equal, A squared H is equal to H. Okay? Well, in the first case, right, this means that H is not equal to any of these, right, if there are 2 cosets, because A or A squared would be a coset representative for some other one. However, if you look, right, what is A times AH? But that's equal to A squared H, right? But that should also equal, by 1, A cubed H, which is the identity, times H, because A has order 3. So that has to be equal to H, which means all 3 cosets are the same. Okay? So that must mean that A is in H. Okay? And so pick some other one of these 2 things, you get a similar argument that shows that no matter what, A is in H. Okay? So this is a contradiction. So 2 and 3 are similar, which means that H contains all elements of order 3 in A4. But we could write those out, and actually there are 8 of them, which is a contradiction. Okay, so I may need to invest in a proper eraser. Okay, but we can list all elements like that. In A4. There are 8. So 1, 2, 3, and its inverse. 2, 3, 4, and its inverse. What else? 1, 2, 4, and its inverse. 1, 3, 4, and its inverse. That's all of them, right? This is 8. H can't contain contain all those. It only has 6 elements, so this is a contradiction. Okay, so what have we shown? We've shown that even though the order of the group A4 is 6, there is no subgroup of order 6 in there. So no subgroup with index 2. And that means that the converse of Lagrange's theorem fails for the group A4. So one conclusion is that A4 is not CLT, or does not satisfy the converse of Lagrange's theorem. And remember what the Lagrange's theorem says. It says that if you have an element in a group, then its order must divide the order of the group. Or you could also say a stronger statement: any subgroup, the order of the subgroup must divide the order of the group. Okay, which isn't true here. Okay, so we did one example. What do you think? If you have any questions, send them to me via email or put them in the discussion forums that I set up on D2L.